Alright, show of hands. Who likes doing really complicated math? Yeah, that's what I thought. Yeah, there's a few of you out there. You like doing complicated math. Most of you, not so much. Me either. Math has never been my thing. I can do math. I was able to plow through my calculus classes at school. Never really clicked for me, but I could do it. And so if somebody comes to me and says, hey, would you like to simplify the math that you're doing? I say, yes, please. And so let's talk about that here. We talk about some approximations that we can use to simplify the math. So when an equilibrium constant is very small, the position of equilibrium favors the reactants. For relatively large initial concentrations of reactants, the reactant concentration will not change significantly when it reaches equilibrium. So, assuming the reaction is proceeding forward, what we're going to do is if we have a relatively small K value and we have a relatively large initial concentration of reactants, we're going to say, yeah, I mean, technically, the concentration at equilibrium is the initial concentration minus some change that happens, but this change is really small. Really small. And since this is a subtraction, you're subtracting that change, that amount of stuff that reacts. Really, the equilibrium concentration is the same as the initial concentration. Like, unless you're getting really, really precise, the equilibrium concentration has not changed relative to the initial concentration. Now again, this is not always going to be the case. This is only the case if we have a relatively large initial concentration and relatively small K value. The general rule of thumb that I use to determine if I should even attempt to use this rule is if the difference between K and the concentration is greater than 4 orders of magnitude, then I will attempt it. If there's less than 4 orders of magnitude difference between the two, so let's say, for example, K is equal to 0.1 and C, the concentration of the reactants, is equal to 0.5. Like, those are way too close together. I would not even attempt that to make this assumption, because the assumption is not going to work. But if, on the other hand, K was not 0.1, but instead maybe 1 times 10 to the, well, I'm running out of space there. If it was 1 times 10 to the negative 6, well then, heck yeah, I'm going to make this assumption, because that is so tiny of a K. Very, very little of these initial reactant molecules are going to react. Some of them will, sure, but I would probably have to have 4 or 5 sig figs worth of precision to see a difference. It's still going to be 0.5 molar at equilibrium, essentially. This, by the way, is what we call the X is small assumption. So, if you remember from the previous video when we were subtracting X from stuff, like right here, so we're subtracting X from 0.2. If this X is really tiny, it's still essentially 0.2. And so when we make the X is small assumption, we're saying anytime that we are subtracting or adding X to something, we're just going to ignore the X. Now, we can't do that when we're multiplying. So here with 2x, we can't just say, oh, x is really small, so there's nothing there. No, that doesn't work. It only works if you're adding or subtracting x from something. Then the x is small assumption is possibly usable. Okay, so let's look at an example of this. So we have the decomposition of H2S. It is decomposing into hydrogen gas and sulfur. And we're given a K value for 800 degrees C, and the problem tells us we have a half-liter reaction vessel initially containing 0.0125 moles of H2S at 800 degrees C, and it asks us to find the equilibrium concentrations of H2 and S2. Alright, so the first thing I'm noticing here is that K is itty-bitty, very tiny, 1.67 times 10 to the negative 7. You can find K values smaller than that, for sure, but it is very small. This is a highly reactant-favored equilibrium. Not very many products are made. And then our initial concentration of reactant, while not terribly high, is way higher than the K value. So it's looking pretty good for our X is small assumption here. Okay, so we went ahead and made our ice table here. I want to point out that they did go ahead and actually calculate the molarity of the H2S because it wasn't given in the problem. We were given the number of moles, and we were given the volume of the reaction vessel. And so they went ahead and divided one by the other to get the molarity, and that's what they plugged in here. And that's usually what you want to do. If the question doesn't specify that it wants a concentration, it could actually want a number of moles. You can actually use a number of moles in the ice table. That works just fine as well. But it does specifically say it wants a concentration here. So they go ahead and convert to concentration at the beginning. Here, they kind of skip past figuring out which direction the reaction is going in. It says by inspection, Q is equal to 0, so therefore the reaction will proceed to the right. By inspection is the sciencey way of saying, obviously, the reaction is going to go to the right. When someone in the scientific realm says by inspection, they're essentially saying you don't even need to do the math. You can just look at it and tell what's going to happen. Okay, so now we're going to input our changes with respect to X. So based on the stoichiometry, once again, we have 2 of this molecule disappearing, 2 of this one appearing or being created, and 1 of this one. So we're going to have minus 2x, 2x, plus 2x, and plus x for our values here, which would give us, at equilibrium, 0.025 minus 2x, 2x, and x. So again, we're just applying that change to the initial concentration. So we are now going to make the X is small assumption. So you can go ahead and read through this text if you want to. I'm not going to read through it. Essentially what the text is saying is this is going to give us a complicated math problem. It's solvable, for sure. It is an equation with only one unknown, so you can solve it. But we're going to make the X is small assumption instead. So they go ahead and they plug everything into the equilibrium constant, including the equilibrium constant itself. And so here we have 4x cubed over 0.025 minus 2x squared. And so again, this is solvable for sure. You can solve that. It just would be kind of a pain in the rear. And so instead, what they're going to say is this we are going to ignore. Not the square, just the 2x there. We're going to say x is small, so the change that's going to take place to this 0.025 is negligible. We're just going to ignore it. And so that then leaves us with just 0.025 squared in the denominator, and with only a single x, or technically 3 since it's cubed. But we just have that 4x cubed in the equation. That's the only x we have. And so this is much easier to solve. Much easier. And so we just bring that denominator over to the left side, multiplying both sides by the 6.25 times 10 to the negative 4. Do that math. Actually, they don't do the math immediately. They go ahead and divide both sides by 4 as well. And then they do that math and take the cubed root which, if, by the way, if you don't remember how to take a cubed root, raise whatever it is that you're taking the cubed root of, raise it to the 1/3. That is the cubed root. And they get 2.97 times 10 to the negative 4 as their value for x. Now, this is where we have to double check to make sure that our assumption is not going to be too wrong to use, essentially. We want to make sure that our assumption is, it's definitely not going to give us the exact correct answer. Any assumption you make is going to mess with your answer a little bit. In this step here, we're just making sure that it's not messing with our answer too much. We're getting close enough. So to check whether the approximation is valid, what you're going to do is you're going to take the value of x that you found by making that x's small assumption, and you're going to divide it by the number you are going to either add or subtract it from. So back here, this is our value for x that we got. Initially, we were going to have, we're going to subtract 2x from the 0.025. And so to determine if our x's small assumption is valid, we take our x value, divide by what we were going to subtract or add it to or from, and then multiply by 100%. If the number you get here is larger than 5%, you're not allowed to make the x's small assumption. Now, for our purposes here, it's just over 1%, and so we say, hey, awesome, 1%. That's a pretty small error. Like, we can live with 1% error, saving ourselves the pain of the algebra. And so we go ahead and say the x's small assumption is valid, and we're going to move on. If, on the other hand, we did not find that, if we found that the number we got here was maybe 7 or 8% or something like that, you would have to go ahead and go back and do the math. Most of the time in this class, I will tell you if you're allowed to make the x's small assumption, most of the time, especially in later chapters. Just to save ourselves the time of one extra calculation, I'll just go ahead and tell you, yeah, that's fine. But I won't always, but most of the time I will. Okay, so then the last step here, we're going to go ahead and take that x value that we found and plug it in to the equilibrium values that we had from our ICE table. And so we have 0.025 minus 2 times the value of x, and that gives us this. And then we have 2x, which gives us that, and x. And those are our equilibrium concentrations. All right, and so then the last thing there, they were just plugging them back in again to double check that the values they got are correct. They plugged it into k to make sure they got the same k value back. All right. I'm going to call it there for this video. In the next video, we are just going to do, I believe, 4 different equilibrium practice problems. So that is all we're going to do in that video. So I will see you there, and hope you will be prepared to work through some of those on your own before watching me work through them.